Imagine a perfectly reversible physical system. An action unfolds, traces a specific path, and retracts back to its exact origin with zero loss of information. An inverse function extracts an initial input, x, from an output, y. Take f of x equals 5x plus 2. To reverse it, subtract 2 and divide by 5. The output feeds into this new equation, mapping flawlessly back to the specific input. But this perfect loop requires a strict mathematical prerequisite to exist. The original function must be what we call bijective. Bijectivity has two parts. First, the function must be injective, or one-to-one. This means every single input maps to a completely unique output. There is no overlapping data. Second, it must be surjective, or onto, meaning no possible outputs are left unmapped by the function. True mathematical inversion requires both conditions. It is a strict privilege restricted only to functions that never repeat an output. This requirement presents an immediate problem when we try to create an inverse for trigonometric sine function across the real number line. This plane plots the endlessly oscillating sine wave. To reverse engineer an angle, let's test a target output of 1/2. A horizontal line intersects the curve at exactly 30 degrees. Again at 150 degrees, and 390 degrees. An infinite number of different angles produce the exact same vertical height of 1/2. Mathematically, this is a many-to-one mapping. The function explicitly fails the horizontal line test. Because the sine wave inherently repeats its outputs, it is mathematically impossible for a global inverse function to exist on the whole real line. To solve this, mathematicians treat the periodic nature of sine as an engineering constraint. We must artificially constrain the domain to force the function to obey the rules of inversion. Looking at the full sine wave plotted across multiple periods, we need to hunt for localized areas where the function behaves injectively. The strategy is to mathematically trim the domain into isolated segments where the curve strictly increases or decreases, ensuring it never repeats a y value. We can find one of these valid segments on the negative side of the x-axis, strictly bounded between -3 pi over 2 and -pi over 2. Within this artificially bounded slice, the function passes the horizontal line test perfectly. We find another valid segment closer to the origin, running from -pi over 2 to +pi over 2. And we find a third segment on the positive side, bounded between pi over 2 and 3 pi over 2. Each of these isolated valid intervals is formally defined as a branch of the sine function. Because the wave repeats endlessly, there are infinite valid branches to choose from. Mathematics requires a single, universal standard to represent the true inverse. To maintain consistency across all calculations, the global mathematical community adopted a specific interval as the absolute default. We isolate the central branch closest to the origin and discard all other infinite possibilities along the x-axis. This specific mathematical slice is defined as the principal value branch. The rule is rigid. Whenever we write the notation for inverse sine, we are permanently hard-coding our outputs to exist only within this specific boundary. With the domain restricted, we execute the geometric transformation. Swapping the x and y axes rotates the segment, forming the new inverse function. This arcsine function has a strict domain limited between -1 and +1. This domain constraint exists simply because the original sine wave's amplitude never exceeds 1 or drops below -1. You cannot ask for the inverse sine of 2 because the original function never reaches 2. The official range of the arcsine function maps directly to our chosen principal branch, running strictly from -pi over 2 to +pi over 2. Arcsine is a strictly engineered machine. It only accepts numerical inputs between -1 and 1, and strictly outputs an angle bounded between -pi over 2 and +pi over 2. Now we can analyze how this engineered inverse interacts when composed directly with the original sine function. This equation illustrates property 1, which states that taking the sine of an inverse sine simply returns the original starting value. We can test this property using a valid input. We plug the value 0.8 into the internal inverse function. The internal operation maps 0.8 to its corresponding unique angle, which we'll represent with theta.
The external sine function then takes that exact angle and maps it right back to the starting value of 0.8. This property works perfectly under one critical condition. The initial input x must fall strictly between -1 and 1. As long as you feed the inverse function valid data within its engineered domain, the composition acts as a flawless, symmetrical mathematical mirror. Property 2 tests the reverse composition. It is incredibly common to assume this reverse operation behaves exactly like property 1, mirroring the input back flawlessly. This assumption leads directly to a classic high-stakes exam trap. Students see the inverse sign applied to the sine of 5 pi over 6 and assume the functions cleanly cancel out to return 5 pi over 6. This intuitive cancellation is mathematically illegal. It violates the domain rules we just engineered. We have to evaluate the inner function first. This graph plots the input of 5 pi over 6 and locates its output on the y-axis, which is exactly 1/2. We then pass that output of 1/2 into the outer inverse sine function. The inverse function attempts to reverse engineer the original angle, but 5 pi over 6 hits the hard-coded boundary constraint. It falls outside the principal value limits. The machine systematically redirects. It finds the legally permitted equivalent angle that produces 1/2 within the correct boundary, resolving to pi over 6. Because 5 pi over 6 lies outside the restricted range, the inverse function ignores it entirely and returns the principal angle equivalent. Inverse trigonometric functions do not blindly cancel out. They are fiercely guarded by their restricted domains, demanding rigorous spatial intuition over raw memorization.